multiply by gamma. Contraction means get smaller. Gamma is bigger than 1, I have to divide by it to get something smaller. And I put Lydia sound asleep and I don't blame her. Yeah, in a Zen kind of a way, right? All right, so guys, here's an interesting thing to sort of pull all this together in a very interesting way. If I take this and I run across the room with it at high speed, what happens to the length of this for you? It decreases. So you're going to see it shorter, right? Everybody's understanding that? You're going to see it shorter.
Is that like the freeway lines when you're going?
No, that's different. So we're not talking about actually we're not talking about your perception is. We're saying the actual length is shorter.
Okay.
It really is shorter for you when you see it moving. It really is. All right. Now.
Does that have to do with why you're longer than you wake up? Because you're not moving?
No, that has to do with the fact that when you're lying down, your own weight doesn't compress your spine. So that's a completely different thing. No, nothing in your everyday life will lead you to these. None of this is everyday life, unless you're traveling near the speed of light.
So how doesn't it? Because when you travel like on the freeway, the lines are bigger, but when you're like actually moving in respect to them, they're shorter.
If you were to take any mechanism we have for measuring those lines, you would rapidly find out they look the same length by that measuring. I'm saying no, you can't find a measuring device that will measure this length that you think it is. It's going to be shorter. It is shorter. It's like if I do this, it will look, if I go fast enough, it'll look half as long, and there's no way for you to tell that it's not half that. It's not like a perception, it's an actual length that's half as long.
When you go to the speed of light?
Not at speed of light, nobody can. But when you're going, there are speeds for which if you go, you'll see it changing by a factor of 1/2. Or 1/3, or, I mean, it approaches a length of 0 as you approach the speed of light. So it's very different than how freeway looks. Yeah.
So going back to the almost close to the speed of light, so you're saying that it can be physically shorter.
Yes, physically shorter. Because here's the thing, every measurement you know how to make will measure it shorter. So, but it means if you could stop it, it would be longer.
So every measurement you take is something.
Anything that moves with respect to you is going to have shorter lengths in the direction of motion. And guys, no, you will never see this in your lifetimes unless they build a spaceship with windows that goes near the speed of light, which ain't going to happen. All right? So these are what we call heuristic thought experiments that we do so you can visualize it. You'll never see this unless you're doing subatomic particle physics at some big fancy research with $1 billion budget.
It's like you're talking math and physics.
All right, I'm going to give you some practical examples here in a second. Yeah.
Why is it shorter? Is it because the way you see it? Is
why
it
does mass have
because-
mass? And that's an interesting question, but there's no answer to it. As it moves faster, it looks shorter to an observer who's not moving with it, but I don't know why.
Does that have to do with the
It just
light?
is.
Or no?
And it only gets short in the direction that it moves. So if I do this, it gets shorter. If I do this, it doesn't get shorter, it gets skinnier.
That makes sense.
If I do this, it gets skinnier because it gets shorter in the direction of motion. If I do this, it gets shorter because it only gets shortened in the direction that you're moving. Right, so this is moving like this stays the same, but it gets shorter. Doing this isn't moving along this, so it just gets skinnier here. It gets skinnier in the direction that it's moving. What's that? But nothing nothing you're going to ever see will show you this. It happens. Yes.
Is it only moving or does it have to be accelerating?
It can't be accelerating because everything in this chapter has to have no acceleration because the special theory of relativity is for non-accelerating systems. Yes.
What does this happen if we don't see it in our?
Oh, it happens in subatomic physics all the time. All right. So when people are using cloud chambers, not cloud chambers, but they're using bubble chambers, and when they're studying, using the high energy labs that they do, they couldn't understand anything they were seeing until they learned how to apply these rules to it, and then suddenly everything makes sense. Everything measures out.
So it's the object that has to move relative to you.
Before I actually, when I tell you it's not going to happen in your everyday life, it happens in your everyday all the time because all GPS systems have to use it or they get wrong locations. Because the satellites going around the Earth are moving relative to the Earth, they have time dilation that if they don't account for it, find you half a mile away from where you really are. Because even though it's a small effect, over the whole size of the Earth and where the satellites are, that small error is a big change in where you're actually located. So the early GPS systems were only good up to about a kilometer. They couldn't find you better than a kilometer, but when they accounted for relativity, then they can actually locate you within meters. All right, so it is, I'm not saying it's not practical, I'm just saying you're not going to see it with your eyes. It's very practical, you have to have it. So, okay, I've got a couple of things I want to try to get through. Except for the one big one I was about to do several times ago. I totally left my mind. Well, I've got one. Oh, and now I remember both. Okay, so here's the situation. I've got a barn, okay, and this barn is 30 feet wide. It's not really a barn, it's a shed, all right? It's got open door, it's got open doors on both ends, all right? So what happens is that you sit on top of the barn, and your really good friend has a pole vault, which is slightly longer than the barn. Yeah, like a big long stick, all right? So I'm going to say the barn, all right, not a pole, because that's way too long for a pole. But he's got a stick, the barn, I'm saying, is 30 feet wide, but he's got a stick that's 40 feet long. Got the picture? And he's very quick, so he runs near the speed of light towards the barn, all right? And you look down and say, oh, he's going so fast that the length of that pole vault is so short that as he passes through the barn, there comes a moment where the entire pole vault is inside the barn, right? Because although the pole vault was 40 feet and the barn was 30, if he goes fast enough, the length is short enough that it entirely fits inside the barn from your point of view.
Yes.
Now you're the one holding it. You're holding your pole vault. Does its length change as you run faster and faster for you? No, because it's not moving compared to you. So in your reference frame, it's at rest with you. It stays 40 feet long. What happens to the length of the barn? I'm running towards the barn. The barn's the same thing as the barn is moving towards me at near the speed of light. What happens to the 30 feet of the barn?
Barn, yes.
It got shorter. So from his point of view, not only does it not fit if he's not running, it fits even worse when he is running. It doesn't fit at all.
No.
How can they both be right? I thought physics had to be consistent, and those are two very... Do you understand that there's two complete descriptions of what happens?
So what's happening?
So first is, what I'm first saying is that for the person sitting on the barn, they see the pole vault shrink and easily fit inside the barn. But for the guy carrying it, the barn shrinks. So the pole vault didn't fit before, and now it fits even worse. How can they both be right? And I've actually talked about the answer near the beginning of class. When I say that something fits, what do I mean? I mean the event of the leading edge of the pole vault and the event of the trailing edge of the pole vault happen at the same time. Meaning they're both inside the barn at the same time. But we already agreed that simultaneous in your reference frame isn't simultaneous in anybody else's reference frame. So the guy carrying the pole vault does agree that there's a time when the front of the pole vault's in the barn, and there's a time when the back of the pole vault's in the barn, but they're just not the same time. But you think it's the same time.
How do we think it's the same time?
Because you see the pole vault is short, so you see the whole thing fitting. So that means there's a time where both the front and the back are in the barn at the same time. But he doesn't, because those two events, what we don't always realize is when meter stick. Meter stick. I measured the length of the book. How many measurements have I actually made? Two. I measured this side and I measured this side. We're so used to putting the zero of the meter stick on one edge that we don't realize that's a measurement. You can't get stuff without making two measurements. So when I talk about fitting in the barn, it's two things I'm measuring. Is the front end in? Is the back end in? That means it fits. But those are two different events, and they don't have to occur at the same time.
How would they occur at the same time?
They occur at the same time in a reference frame if they both happen to be in there from your point of view. So my glasses fit inside the room from everybody's point of view here, but I guess if they were going through, if somebody was carrying really fast, this room wouldn't be big enough to hold my glasses. So we would say, well, the front edge and the back edge happened, but they didn't happen at the same time.
I feel like we need to see like something in order to be able to.
If I could run the pole vault for you, not only would I do it, I would make so many records obsolete. I cheerfully do it. All right. So now the other thing is, and I'll try to tell this story kind of fast. This is a real story. All right. So it's not pole vaults in barn. So there's a mountain in France called Mont Blanc, which is one of the tallest mountains in Europe. And because of that, there's a lot of experiments they do at the top of the mountain because of the fact they're well up above a lot of the atmosphere and other things. So it turns out there's some particles called muons that are created by cosmic rays colliding with the atmosphere, and they produce these little particles called muons, which are like electrons, right? And so these electrons, electron-like particles, are moving at near the speed of light. So, but they also have a half-life, they decay. What they do is they put a big detector at the top of the mountain, and they measure the number of muons that arrive per second, per minute, whatever, right? So they get a rate at which muons are arriving. So not only do they have the number of muons that are arriving, because of the way they capture them, they can see how fast they're going. You with me? So we know how fast they're going, we know how many are arriving. We also know how tall the mountain is. We know how fast they're going, we know how tall the mountain is, we know how long it's going to take them to get down to sea level. You with me? So we put detectors down at the bottom of the mountain. And we say, based on how fast they're going, based on what their half-life is, we can figure out how many ought to make it all the way to the bottom of the mountain. Does that make sense? So we know the rate they decay, I know how many are right here, I know how long it's going to take them, so I should figure out how many ought to make it to the bottom of the mountain. And I go down and I count the bottom of the mountain. And way too many make it. Why? Because when the muon is born, it's got a little clock and says, you can live for 10 microseconds. And because he's moving fast compared to me, his clock runs slow and he lives too long. So they make it. But from his point of view, his clock is just fine, so why does he think he makes it? Because the mountain is short. Because as he moves really fast, it looks to him like the mountain's coming towards him, so it makes the mountain short. Sure, in this amount of time I can get to the bottom of that short little mountain. What's really cool is both those descriptions give the same answer to exactly how many muons actually make it. This is not fairy tale stuff. It's actually the way we explain observed science. It's cool. It's confusing, but cool. All right, so we will go over this more. I want to get a whole bunch of thoughts out there today so that you have enough to start saying, what on earth did I get into? And then we'll try to tidy it up a bit as we go, all right? So I will see you on Friday. And the homework is up. Please do a couple things to check for me. Kit, check to be sure that your assignment on 17 is gone. All right? And guys, check to be sure that all the globals are right, that you actually have the time you think you have, that you have infinite tries, and let me know as soon as possible because I don't want to be messed up again. Is there more? Is there more?